You've heard of ChatGPT, right? You've seen all the incredible things AI can do, but have you ever wondered what's actually under the hood? What's the engine that makes it all possible? Well, it's the GPU. And let me tell you, it's not just for video games anymore. It is the fundamental piece of hardware driving this entire AI revolution. So let's dive in and demystify the most important chip in the world right now. So here's our game plan. We're going on a little zoom in, zoom out journey together. We're going to start at a really high level, then we'll dive deep, right down into the silicon to see how a single chip works. And then we'll zoom all the way back out to see how thousands, yes, thousands of these chips get wired together to build the supercomputers that train today's AI.
All right, first things first, let's start with the basics. When we're talking about AI and machine learning, what is a GPU, really?
At its absolute core, a modern AI GPU is all about a powerful partnership. Think of it like this. You have a team of hundreds of small, super specialized brains. These are called Streaming Multiprocessors, or SMs for short. And sitting right next to them is their own personal, incredibly fast memory, called HBM. The HBM's only job is to constantly shovel data to those brains so they can keep on working. This duo, the SM and the HBM, that's the magic formula. It's the building block for everything else we're about to talk about.
Okay, now for the fun part. Let's pop the hood and really zoom in on a single one of these GPU chips. And to make things a little clearer, we'll even compare it to its famous cousin, Google's TPU, the Tensor Processing Unit. Now, this table is like a little cheat sheet, but what it really shows us is a fundamental design difference. See, a GPU is built with hundreds of these smaller, flexible streaming multiprocessors. A TPU, on the other hand, usually has just one or two absolutely massive, super powerful cores. This modular design is what makes the GPU such an amazing general-purpose tool. It can juggle hundreds of different jobs all at once.
And this is that core brain we keep talking about, the SM. On a modern NVIDIA H100 chip, there are 132 of them, 132 independent programmable units. That's the GPU's superpower. It's like having a factory with 132 separate assembly lines that can all be working on completely different things at the same time. The flexibility is just incredible.
Of course, what good are 132 assembly lines if they don't have any parts to work with? They'd just be sitting there, right? Well, that's where HBM comes in. It's like a gigantic, lightning-fast workbench sitting right next to all those brains. It holds all the raw materials, the model's data, its weights, its activations, and gets them to the compute units with almost zero delay. That speed is absolutely non-negotiable for modern AI.
We've seen the chip. Now let's get our magnifying glass out. We're going to zoom in even further. I'm talking down to the microscopic level to see what makes a single one of those 132 streaming multiprocessors actually do its job.
So check this out. Each SM is basically its own little factory within a factory. It's split into 4 identical sections. And inside each of those sections, you've got 2 key pieces of machinery. First, the heavy lifter for AI, called a tensor core, and second, a more flexible set of tools called CUDA cores. And a little manager, the warp scheduler, makes sure they're all working together perfectly.
Okay, pay attention, because this right here, this is the main event. The tensor core is pretty much the reason NVIDIA GPUs dominate the world of AI. See, deep learning, when you strip it all down, is just a ridiculous number of matrix multiplications. And the tensor core is a piece of hardware built for one thing and one thing only: to do that one specific type of math and to do it insanely fast. And if you want proof, just look at this chart. It is just wild. On an H100 GPU, the tensor cores give you almost 1,000 T-flops of power. A T-flop is 1 trillion calculations per second. It's a mind-boggling number. Now look at the more general-purpose CUDA cores. They top out at 33. That is a 30-to-1 difference. This tells you everything you need to know about where the engineering focus has been. It's all about making that AI-specific math fly.
But hold on. That doesn't mean the CUDA cores are just sitting around doing nothing. Not at all. They are the versatile, do-it-all workers. They come from the GPU's history in gaming, and that flexibility is still absolutely essential. They handle all the other little jobs in an AI model that aren't pure matrix math, like activation functions. You can think of it like this. The tensor cores do the heavy lifting, and the CUDA cores handle all the important details.
Okay, deep breath. We've been way down in the weeds of a single chip. Now it's time to zoom all the way back out. Because a single GPU, as powerful as it is, isn't enough for modern AI. We need thousands of them. So how on earth do you connect them all together to act like one giant brain?
Well, the key to understanding this is to think of it like a city's road system. You've got these super fast, private little roads for getting around your immediate neighborhood. And then you have the slightly slower, but much bigger public highways that connect all the different neighborhoods together. This two-level structure is absolutely fundamental to making these massive systems work efficiently. So this is your local neighborhood. It's called a node. It's a tight-knit little group of 8 GPUs, and they're all connected by a private, super-fast highway called NVLink. Communication here is basically instantaneous. These 8 GPUs are like best friends living in the same house. They can talk to each other without any delay, which makes them perfect for tasks that need a ton of constant chatter.
And you can see that speed difference right here, plain as day. Inside that 8 GPU house, data is flying around at 450 gigabytes per second over NVLink. But to talk to a GPU in another house, another node, you have to take the public highway called InfiniBand. The speed drops a little, to 400 gigabytes per second. Now that's still ridiculously fast, but that 50 gigabyte per second difference is a big deal, and it's something AI developers have to very carefully plan for.
So if the node is the local neighborhood, the superpod is the entire city grid. This is the architecture that connects all those individual 8 GPU neighborhoods together using that big InfiniBand network. This is how you get to that mind-boggling scale, linking thousands and thousands of GPUs into one single cohesive supercomputer.
Okay, so we've got all this insane hardware, a city of GPUs all wired together. But this next part answers the most important question of all. So what? How does this very specific design, the SMS, the HBM, that two-tiered network, actually affect how we train AI models in the real world?
I mean, this is the million-dollar question, isn't it? Just because a GPU has this massive theoretical top speed doesn't mean you can actually use it. Real-world performance isn't just about raw power, it's about a very delicate balance. A balance between thinking and reading. Let me explain what I mean.
There's this concept called arithmetic intensity. It sounds kind of academic, but it's actually pretty simple. Just think of it as the ratio of thinking to reading. A GPU is happiest and most efficient when it can grab a small chunk of data from its memory and then do a ton of thinking, a ton of calculations on that one piece of data. If it spends all its time running back and forth to memory just to do one simple calculation, it's wasting almost all of its potential. It's stuck waiting for data.
And this abstract idea has a very, very real number attached to it. For an H100 GPU, that magic number is about 2,500. To keep an H100 busy thinking, instead of waiting for data, you need to give it a batch of at least 2,500 tokens to work on at once. If you go below that number, the GPU starts to get bored. It spends more time waiting for its next meal than actually chewing on it. The hardware's design literally dictates the software strategy. And this leads directly to these real-world rules that developers live by. Want to split your data across a bunch of GPUs? Well, you'd better make sure each one gets a big batch of at least 2,500 tokens. Want to split the AI model itself into pieces? It's way more efficient to do that inside that local neighborhood of an 8 GPU node to use that super fast NVLink. You see, the hardware isn't just a blank slate. It gives you a rulebook for how to train your models effectively. Wow. Okay. We have covered a ton of ground, all the way from the guts of a single processor core up to 1,000 GPU supercomputer. So let's bring it all home with one final thought. The modern GPU is this incredible masterpiece of balanced engineering. It's a constant, delicate trade-off between three things: raw computing power, fast memory access, and high-speed networking. But here's the thing. AI models are getting bigger at an exponential rate, and that's putting an unbelievable strain on this balance. And that leads to the ultimate question for the future of AI. Which of these three pillars, the on-chip compute, the on-chip memory, or the network connecting them all, which one is going to be the first to crack? Which one will become the bottleneck that limits our progress? The answer to that question is going to define the next generation of AI.